Hey, good afternoon. Today's our last lecture in terms of material that we're gonna cover for the semester. On Wednesday, we're gonna have our review for the exam that we have on Monday. And Monday next week is gonna be our last day. So that's the plan. Any questions? Yes. Yes, so the final is not the third exam. The third exam everybody has to take. The final is scheduled for it's scheduled by the university and is optional. So what that means is if you're happy with your grade after you take the third exam, what's gonna happen is I'm gonna grade the exam and then I'm gonna post all the grades for you. And you will have a course grade based on those items. And then if you are happy with that grade, then you don't have to come for the final. But if you are, let's say you are in the 79 or 89 or 88, and you want to see if you can improve your grade, go to the next grade, then I will encourage you to take the final, because with the final, you adjust the weight of some of the items, and the final can help you, if you do well in the final, can help you improve your grade. No, all of them will be counted. Yes, all of them. Yeah, so there's no elimination, but my experience is for those students that take the final, and if they are close to the next grade, typically they'll do very well in the final and will go to the next grade. What? Yes, yes. So the final exam is comprehensive. So if you want to study for the final, you can just go through the three reviews that we have during the semester. Yeah. Any other question? The final, yes. So the two exams that are left, both of them are going to be online. Yes. Yeah. Bless you. So today's lecture is a continuation of what we started discussing on Wednesday for the facility location models. So on Wednesday, we introduced the concept and also the questions that we wanted to answer, and we discussed all the variables that were taken into consideration when you were making decisions in terms of where to place the next facility. So as I mentioned on Wednesday, we started this class discussing the design of a facility from the inside. And then we cover all the topics that were associated with the design of the facility from the inside. Last lecture, lecture 11, transition from the facility to the warehouse. And then now in this last lecture, we are looking at the problem of location. So a facility from a location point of view. So if you have these many customers, or if you have these many, let's say, stores, and you want to open the next one based on, the location of the other stores and the location of your customers, how do you make a decision on where to place the next facility? Sorry about that. So on today's lecture, we're going to go back to formulating the problem from a mathematical perspective. So an optimization model, and then I'm going to present an algorithm for solving that problem. And I'm going to present an example, and then that will be the last part of the lecture. So we are now looking at the principles of facility location. So again, the point of view of making decisions on where to place the next facility, given that you have a set of customers or a set of stores that you have to supply. So these decisions are typically made in terms of considering an objective function that is guiding your decision. So for instance, you want to take into consideration not only the distance from this new location to all your customers or your other stores, but also the frequency of the trips that you are going to make to those locations. So location can be very close, that will be good in terms of distance, but if you don't have a lot of interaction with that store, that could outweigh the benefit of getting another or placing the facility closer to another store where you have a lot of interaction or you have a lot of movement happening. So it's you can see it from a perspective of trying to optimize multiple performance measures simultaneously, like distance plus the flow that is happening between this new facility and your existing facilities. So, so we're going to focus on this single facility location model. That's typically how decisions are made. You're not planning unless you're going, let's say, to move to another country. Typically, you are adding a facility at a time. You add this facility, you're upgrading your network, your supply chain, you see how everything goes, and then you move to the next one, especially if you are looking at a specific region. If you're looking at multiple regions, then the problems are independent. Right? You're optimizing for this region, you're optimizing for this other region. But the single facility location model is typically what we do. So in this lecture, we're going to learn and analyze facility location models. And as an introduction, this is a pictorial or a figure that is trying to illustrate what we are trying to do. So there are different types of models. The one that we are going to focus on is the single facility location model in this lecture. But there's a location allocation model and the quadratic assignment model. They're looking at the same problem from different perspectives. So the idea again is you look at the location of your customers, and then you're trying to make a decision on where to place the next location so you can improve that performance measure that is guiding your decision. So let's look at the single facility location model, and we talked about it a little bit on our previous lecture. So there are two types of objective functions. Again, the objective function is what's guiding our decision. So there's the Minisum location problem, which is trying to minimize the summation of the weighted distances between the new facility and other facilities. And the minimax location problem that is trying to minimize the maximum distance between the new facility and any existing facility. So the minimax location problem is the type of problem that you would try to solve if you, for example, are trying to locate the next fire station. So you are trying to minimize that maximum distance so you can cover more of the area, right? So if you have let's say 10 different neighborhoods and you're trying to put the next fire station, you want to make sure that that is located so you can cover all of these neighborhoods as well as possible. Typically, you have an amount of time that you have to respond for an emergency. For our facility location problem from a manufacturing perspective, we are trying to minimize the summation of weighted distances. So flow times distance between the new facility, because from our point of view, I mean, traveling long distances is going against our efficiency. It takes too much time for us to supply our customers, and also there's an additional cost, right? The fuel that you have to spend to the trucks and so on. So in this problem also, we look at different type of ways of measuring distances. So this is what we call the rectilinear distances. These are typically used because they are easy to measure, right? If you were to solve this problem, like right now, you have access to multiple sources of information like Google Maps or other ArcGIS software. If you wanted to look at the distances taken into consideration, like for example, the actual roads that you would travel to, you can also do that. But the decisions actually are not changing too much. So rectilinear distances become very accurate in terms of making our decisions. So rectilinear distances, typically, this is what we do. We consider the area as a area in X and Y axis, and then we find the coordinates for each one of the points, and then we compute the distance based on the location from the y-axis and the x-axis in this Cartesian plane. So distance, if you were to look at, let's say, the new facility is in red here in this figure, and the existing facilities are the ones in yellow. If you want to find the distance using a rectilinear distance from this red dot here and this yellow point, then you're looking at the absolute value between the, for the x, between the point where the new facility will be located and the x coordinate for the location of the existing facility. And that will be the difference of it, the absolute value of it, plus the same thing here, but for the y-axis, the location of the new facility or potential new facility, and the y-axis for, which in this case will be BI, for this existing facility. So the summation of the absolute values of those differences will give you the distance. And we will use the distance for each one of them. You'll see if you have these many yellow points, you will have to find distance between each one of them. So that's how you compute it, and then the weight is going to be equal to the number of trips. So as I mentioned already, is a multi objective type of objective function, because we are now not only looking at the distance, but also at the number of trips, which will be our weight. So what I mentioned already, like if you have a high volume of trips between two locations, you want to make sure that you locate closer. You're located closer to that node. But if you don't have a lot of interaction between a store and the new location, then you don't necessarily have to be located close to that store. And that W, which is the weight, is what's going to guide that decision. That W is going to be very small if you don't have a lot of interaction with that existing store. It's going to be high if you have a lot of interaction with the store. So the weighted distance is going to include that parameter W in terms of computing the objective, right? So now you have WI times the location of these, or the distance between the new facility and the existing facility, I, plus the weight also multiplied by the distance in terms of the y-axis. So for the Minisum location problem with rectilinear distances, we have these objective function. So as you see at the top, we have the summation for WI times the difference in terms of the distance, plus for X plus WI times the absolute value of distance difference for Y. And this goes, I mean, you have to compute this for every every distance from the new facility up to the each existing facility. So what this is showing is that we can separate this objective function. So the steps for separating this is you can separate the minimization, split it into two components, one looking at the X part, and then another piece looking at the Y component. So you are looking at, in terms of the X-axis, trying to minimize that distance, and then also minimize the distance in terms of Y. So you can separate it into two independent problems. Okay, one that is going to focus on the distance from the X perspective, and one that is going to focus on distance from the Y perspective. And the idea with separating this objective function is that we can develop an algorithm to solve the problem without having to use a commercial software to solve the mathematical formulation. And that's what we're heading to. So we take the formulation, we understand the formulation, but we are not solving the problem using a computer software. We're run an algorithm that is gonna give us a good solution. So let's look at this example. So here we have facilities 1, 2, 3, and 4 located at points A5, 4, 2, 11, 8, and 13 and 2. And it's estimated that there will be 9, 6, 4, and 12 trips per week, respectively between the facilities and a proposed new facility. So the question is, if you have this information, where would you locate the next facility? Okay, so remember, it's not just about the distance, but also about the weight. So you have to use these weighted distances in order to make a decision. So in terms of formulating this objective function, as you can see here at the top, we can use these parameters and build this objective function. So you see, we have the X coordinate for each facility, we have the Y coordinate for each facility, and we also have the weights, which are the number of trips between the new facility and the existing facility. So for facility 1, we have 9 trips. So our W1 is gonna be 9. Between facility 2 and the new facility, we have 6 trips, so W2 is gonna be 2, and so on. And then we formulate the objective function by substituting these WI values for the corresponding facilities, and also substituting the values for AIs, remember, the AIs, X minus AI, and then Y minus BI. AI is gonna be the coordinates for the X values or the location of the facilities. BI are the coordinates for the Y axis. And this is how the objective function will look like. So if you were to solve this problem, obviously we are missing some of the constraints, but our decision here is in terms of X and Y, what are going to be the coordinates. So if I solve this problem, I want to find the decision variable X, and I want to find the decision variable Y. Solving the problem will give it those decision variables. It's gonna be only one solution, and it's going to give you a solution in terms of a value for X and a value for Y. But the problem will iterate. It's going to look at all possible combinations that are going to meet the constraints, and it's going to give you the best one. So we can reformulate this. I mentioned already, we can separate these objective functions, or the objective function. If we let this X minus AI being equal to Ri plus Si, then we eliminate the need of having this absolute value, which simplifies the solution of the problem. And that's the substitution that we are trying to do here. So you see, X minus AI, we are making that equal to Ri minus Si, and that's going to be equal to each one of the I value is going to correspond to each one of the existing locations. So we are substituting out those values by that, and then the constraints are going to force this part right here is enforcing those equations to be equal to the original values of the AIs. So for example, for the first X, for the first facility, this was X minus 8. So when we perform this substitution, we are making this equal to this. Ri and Si are going to be new decision variables. So we are trying to solve the problem in terms of these 3 new decision variables, X, Ri, and R1 and S1, R2 and S2, and so on. But we are forcing this substitution to be equal to 8 because that's the value of the original value for the coordinate of the existing facility. Then equal to 4, equal to 11, and equal to 30. And that's in terms of X. We can do the same thing for Y. And we separate the problem. So we have an objective function now for just for X. And we have an objective function just for Y. And we follow the same procedure. We are making the substitution here to eliminate the need of having the absolute values by bringing in this Ri plus Si, but now in terms of Y. So if you look at this objective function and compare with this one, Y minus 5, we are forcing this new substitution to be equal to 5, which is the value of the original coordinate for 1 in terms of Y. Next one is 2, 8, and 2. So 2, 8, and 2. Okay, so I'm not going to ask you to go and solve this applying, for example, the simplex method. That's not the idea. Yes, sir.
You're talking about R-I-I.
Yes.
Where do those values come from again?
Yeah, so it is a modeling trick, basically, because if you look at the original objective function at the top, you see that there are some absolute values happening in those multiplications. So that, in terms of solving or finding a solution to the problem, those absolute values make the problem very difficult to solve. So what we are trying to do based on this principle is that we know that we can separate this problem in terms of X and Y. So we can solve the problem only for X and solve the problem only for Y. So we know we can separate this model into two pieces. So under that, that's what we're trying to do. So in order to make things easier for us in terms of solving this problem, we're going to separate it. Okay, so we focus only on X and also in Y. So we're going to have two objective functions, and then we are going to use this modeling technique to get rid of the absolute values. So instead of just having the objective function that we are trying to optimize, now we're formulating the objective function with additional constraints that are going to give us the same solution, but it's going to make this modeling substitution is going to help us solve this problem easy. Okay, so we don't have to deal with the absolute values. So substitution is making the absolute value of this difference equal to Ri plus Si. These are two new decision variables that we are formulating just for the purpose of the problem. And Ri, so we have X, and then the absolute value is going to be equal to the positive. Without the absolute values, we are making it equal to Ri minus Si. And then we know that both of them have to be greater or equal to 0. So in providing this, so we are substituting everywhere that you see an absolute value, we're going to substitute Ri plus Si, which is what's happening in the objective function. And then originally, if you see the objective function at the top, we have X minus AI, right? Which is what we have here. So what we are, by making sure, let's see how to put it. So that for this to be able to give us the right solution, we need to make sure that we force this difference, X minus A, being equal to A, because that's the parameter for the original coordinate for AI. So essentially what we are trying to do here is to set up the problem so we can solve it easily. And you'll see that under these circumstances, by reformulating the problem, we can apply an algorithm that will give us the solution, which is what we're heading. But that's the idea. We have these two substitutions here. The absolute value equals Ri plus Si. So we are substituting that into the objective function for X. And then in order to make sure that these summation stay consistent with the original value of the coordinate, we're adding these constraints. So, so we enforce those difference and those summations to make sure that use the right value for the coordinate of the existing facilities. And we do the same thing for Y. Okay, so I mentioned here, you can use your favorite LP solver, Lindo, Cplex, or Excel to solve this, but that's not part of these. I mean, solving these type of problems is not part of what we teach in this class. For IE, if you are industrial engineer program or you're a student in the industrial engineering program, you should know how to solve this in Excel or using Ample or Express. But for those of you, which are the majority in this class right now, manufacturing, I don't think you're trying to solve these type of problems. So what we are going to do is we're going to teach you how to solve it, but using an algorithm. So let me just go straight here. So if you solve this in using a commercially available software, you'll get the solution in terms of X, which is coordinate 11. The objective function will be 93. That's the minimum weighted distance that you will obtain for this problem. And in terms of Y, you'll get 51, and the coordinate is going to be 2. So the optimal solution will be 11 and 2, and the total cost will be the summation of the objective function for X, 93, plus the objective function of Y. Okay, and this will be the optimal location. It will be in that point right here where the two lines are crossing, coordinate 11 in terms of X and coordinate 2 in terms of Y. Okay, so how do we get into this solution? You can actually solve this problem using the cumulative weight algorithm. So I want to make a comment before moving forward. So in the previous lecture, we discussed some strategies also to solve this problem. If you don't remember, I would recommend you to go and look at the discussion that we have. And this is called, and we cover a weighted method also for solving the problem. So you need to understand the differences between the algorithms that we have covered. Because in the exam, I will state, okay, solve this problem using this algorithm. If you solve the problem using a different algorithm, it's going to be incorrect. Okay, so you'll get a different solution as well. So if I ask you to solve the problem, make sure that you understand which algorithm I'm referring to, so you use the right technique when solving the problem. So this one is called the cumulative weight algorithm. And what we do is that for each facility, we identify the AI values, which are the existing coordinates for X for each facility, the VI values, which are the existing coordinates for each facility in terms of Y, and we also identify the weights, the WIs. So in this case, we know there are 9, 6, 4, and 12. So we are going to solve the problem also in separate ways. So first, we're going to find X, or the X value for the new facility. And then we're going to find Y. So what are the rules to determine the optimal value of X? So this is for the X coordinate. We are going to arrange the AIs in increasing order. We're going to compute the sum of weights or trips for each value. And the optimal X is the value at which the cumulative weight is going to be greater or equal to 1/2 of the sum of the weights. The rules for determining the optimal value of Y are the same, but you are going to arrange, instead of the A's, you're going to arrange the BI's in increasing order. You're also going to compute the sum of the weights for each value. And the optimal Y is the value of which the cumulative weight is greater or equal to 1/2 of the sum of the weights. So let's start with solving this problem for X star, right? So we have the information that was supplied. And as you can see now, the facilities are sorted according to the value of the coordinate, AI. So we go from 4, which is the smallest value, up to 13. So we are sorting the facility. So 2 goes first because the coordinate AI is 4, and then follows 1 because the coordinate is 8. Then follows 3, coordinate is 11. Then follows 4 because coordinate is 13. So we have the sortation here. And you can see the trips, which are going to be the frequency in which you're traveling to that facility. The WIs are sorted based on the AIs as well. So you see you have a 6, a 9, a 4, and 12. So those are not sequenced according to the size of the number. They're sequenced according to the coordinate. Okay, so when you're doing this sorting, you're going to sort for AI, and the rest of the table will be orderly. Okay, so, and then using the WIs, you're going to start summing the weight. So this last column is the aggregate values for each row. So you start with 6, and then 6 plus 9 is 15. 15 plus 4 is 19, and 19 plus 12 is 31. So this is the key. If you know how to build this table, then the rest is simple. So first thing you're going to do is just sorting for X based on the values of AI. So if you can sort that in an increasing way, and then the last column, after you sort, you can build the last column, which is the sum of the aggregated weights, 6, 15, 19, and 31. So based on this, we are going to find the optimal X is the value at which the cumulative weight is greater or equal to the sum of the weights. So the sum of the weights is going to be 31, and it's 1/2 of that. So that value is going to be 15.5. So knowing that, we know the value that is greater or equal to 15.5 is going to be 19, which means now our coordinate for the problem in terms of X is going to be 11. Okay, so that's the solution in terms of X. So that's why, I mean, if you do the sorting correctly, summation correctly, then you just compute this number, which is the 31 that we got for the sum of the weights, last number, divided by 2, you get 15.5. That's going to be the threshold that you have to pass in order to identify the coordinate for X. In this case, 11. Any questions? Oh, no, it's the value right after crossing the threshold. Okay, so that will be 19. Yes. It is, that's a very good question. So the right way to answer your question is that's the way the algorithm was designed. But by dividing it by 2, remember that you're trying to find a location that is going to be optimizing your trips to most of the, or all of the existing facilities. So if you think about it, that should happen in between the location of the weights, right? The aggregated values of the weights, because if the total weight is 31 and you're trying to balance, like if you go all the way down, you're going to be penalizing the one at the top. If you go all the way to the top, you're penalizing the ones at the bottom. So if you find a value in between, kind of in the middle, which is what this is trying to do, then you're going to be locating the facility close to most of them. And that's the insight of why this works. Good question. So 11 will be X start. We're going to do the same thing for Y. So we, instead of, well, we're going to sort this based on the coordinate BI. And as you can see for BI, we have a tie, right? So 2 and 2 for facility 2 and 4. So typically you will break the ties based on the I value. So smallest I value goes first, the highest will go next. So that's why we have, even though they have the same coordinate, we put 2 first and 4 next. And then we have coordinate BI for facility 1, which is 5, and coordinate I for facility 3, which is 8. So after sorting, you will get these weights sorted in this way. So repeat the process. You do the summation of the weights: 6 plus 12, 18, 18 plus 9, 27, 27 plus 4, 31. And we got the same total, right? Because these are the same weights. If you remember from previous slide, should be the same value. For the weights are not changing. At the end, the total will be the same. But the aggregated sums are different, right? So 6, 18, 27, 31, 6, 15, 19, 31. Okay, so we do the same thing. We are looking for this threshold, right? So 15.5. So what will be the value that will cross that threshold? That will be 18. So 18, that means that our coordinate is 2 for Y. So the optimal location for X and Y is going to be 11 and 2. So let's see how this compares with this. You remember the software solution, right? This is not using the algorithm, but putting these problems into the optimizer. We got X equals 11. We got Y equals 2. So the algorithm works. By solving the problem using the algorithm, we don't have to rely on solving it with a computer or a software package, commercially available software package, which is the nice things about these algorithms, that they give you a quick solution. You're solving this, they're practical. You don't have to spend money, thousands of dollars in a software package. If you have more locations, this is something that you can just put in an Excel spreadsheet, sort, do the summation, find the solution. So that's a nice thing. And these are typically what we do, the type of things that we do in research. So if you're not familiar with research, we all faculty members here in industrial engineering do research. Every faculty member in the English School of Engineering do research. And I know every engineer will be trained to solve problems, and solve problems in industrial engineering and so on, depending on your degree. The challenge is, how do you make things easier, right? So anybody can solve the problem, put it in a computer package and get a solution for a computer package. But how do you design the algorithm behind the computer package that can give you a solution quickly? And that's the type of things that we do when we do research. We find ways to solve problems more efficiently. So, for example, this algorithm was part of a research from a faculty member. I don't remember from where, but yeah, a few years ago. So these things can be disruptive in terms of saving money, right? Because companies doesn't have to go and spend money for solving this problem in particular. And so hopefully, I mean, that capture your interest. If not, then that's fine. I like research, so that's why I bring it to the conversation. Any questions? That's a good question. So in general, heuristics are not getting, this is a heuristic. That's what we call algorithms that are used to solve problems like the ones that I show you, the mathematical problems. So there's no guarantee that heuristic is going to give you always the optimal solution. However, they will provide you very good solutions, if not the optimal. So even if you don't get the optimal solution, the solutions that they will give you are good, so you can implement them. So what's the trade-off is, do you have time to wait for a solution? Because sometimes if these problems are very big, you have to put it into a software, and it will take days or sometimes months to get a solution, the optimal solution. But if you solve it with an heuristic, you can get the solution quickly. It will not be the optimal, but it's going to be a very good solution that you can use in a practical setting. So the question is, do you have time to wait? Most of the time with industry-related problems, that's not the case. So that's why creating these methods are important. Good questions. Any other question? Yes. Yes. These values. So the weights, like when you do the sorting, remember that you're going to do it based on the coordinate. So you go for the smallest one to the largest one. And that's going to affect the order of the weights, right? So it's going to be 6 first because that's the weight for facility 2. 12 next because that's the weight of facility 4. So once you get this order, this right order or the correct order, when you do the sum is going to be impacted by this sorting right here. So 6 plus 12 is 18, 18 plus 9 is 27, 27 plus 4 is going to be 31. Okay. And right there is where the magic of the algorithm is, in this sorting of the weights. Yes. It passes that threshold. Yes. Yes. Yes, sir.
I don't know if I missed that. I know we got data. Was WI, was that given?
WI is given. Is the amount of trips that are happening or will happen with the new facility in place. Yes. Good question. Any other question? Good. So that's the last topic for today. So if you do all this, if you substitute the values, you'll see you will get the 144 for the objective function. And that's it. So if there's no other questions, then we'll stop here. On Wednesday, we'll go over the review. We want to start preparing for the exam. Everything starts in the lecture for material handling equipment. So from that point on is the material for the exam. On Wednesday, I'm going to give you more information. No questions, then I'll stop here. I'll see you on Wednesday.